Morning, everyone. So, yesterday we had started our energy chapter, looking at concepts of work. So far, we found two definitions for work. Work is either defined as a force that's parallel times the distance, or work, as we're going to see more so in the coming days here, work is a thing that causes energy to change. Even though energy should be conserved overall, E in should equal to E out, if I have any non-conservative work, non-conservative forces, that can actually change the energy just like the impulse would change the momentum. So far, I've only introduced to you one type of energy, which is kinetic energy. We did a derivation last day. This one here is on your formula sheet. Kinetic energy is the moving form of energy. Things that move have kinetic energy, and it's related through 1/2 mv squared. Today, my goal is to introduce to you the second main type. Together, these two types are called mechanical energy. Mechanical energy is like energy of moving parts, energy of objects when we're doing kinematics, motion sort of studies. And basically, we're going to match up kinetic energy. We're going to match it up with a guy called potential energy today. So potential energy in general refers to a stored amount of energy. Stored energy can come in many different forms. It can be stored as chemical energy. It can be stored as electrical energy. It can be stored inside our foods that we eat. In this case here, we're going to store energy. We're going to look at the gravitational type. We're going to look at objects that are lifted off the ground. The reason why they have the capacity to do work is because they've been storing, saving the energy in lifting, and then when you drop the object, it can now end up falling. So potential in general talks about stored energy. It can be many different forms. We're going to focus specific on the gravitational type. So we're just going to call it gravitational potential energy. Sometimes they call it GPE. And we're going to do a quick derivation here. For gravitational energy, it's objects that are off the ground. We still will need the kinetic energy formula later on as well, so don't forget about that. But specifically, we want to introduce this potential energy concept. So in this case here, the derivation is a lot more simple. We're going to have a mass that's on the ground. Right now, if I just run the clock, this object here is just going to end up just sitting there. It's not doing anything. So in this case here, it has no stored energy. I'm going to say EP is actually 0. Now I'm going to come along here as I'm going to lift up this object here. As I lift up this object, as we get farther and farther away from the ground, I'm actually storing more and more energy into this object here. What we're going to be measuring, mechanically speaking here, is how high off the ground am I lifting it up. The higher it is, the farther it has to drop, the more force it can apply over that distance. I'm actually storing more energy. I would expect potential energy has some relationship with this H here. So like I mentioned, the derivation is fairly simple here. We're going to start off with a really simple picture. Let's imagine that there's no acceleration. So we're going to do this in a later question as well. Looking at a free body diagram, we know there's gravity. Gravity is Fg, which is mg. I'm going to imagine pulling it up so slowly that it exactly counteracts gravity. So this is my applied force, and I'm just going to pull just hard enough to make the net force 0, to let this go at constant velocity. I know constant velocity could mean 0 meter per second, but let's say this one here is actually speeding upward at a constant velocity. Okay, so I am, maybe I'm holding it with a crane of some sort, and I am lifting the object upwards. My force that I'm applying happens to be mg. I'm going to be applying it over a distance of h, because the definition for work is equal to F times D. The force is upwards, the distance is also upwards. I'm just calling it h. We're going to have the force is actually given by mg times d, and I'm just going to rename that d there to h. And therefore, I'm going to have two situations here. I'm going to have a potential energy when it's this far up. It's going to be given by mgh when it's final, or I'm going to have mgh when it's initial, when it's back on ground level. Because work is also a change in energy, it's a change in heights in this case here, it would be mgh final minus mgh initial, or if you like, you can go mghf minus hi. So basically, the amount of elevation I end up lifting this object upwards, that's how far pulled upwards it is. I'm just going to define this first term here as your potential energy final, or your potential energy initial. Up to you. You can do the notation like PE or E subscript P, but make sure you can track which one's final and which one's initial. As we just start introducing this formula here, I want to introduce you the idea here. It turns out H equals 0, what we're going to call the ground level. We can set the ground level to wherever is convenient. Now, on this problem here, there is only one ground. It makes sense to set H equals 0 here, so when the object is sitting there, it's going to be 0. But we're going to find in the next question and questions coming up, sometimes it might be helpful to set H equals 0 up here, because we just have a relative delta H term over here, a relative how far off the ground I'm at, based on whatever I call 0, I can now use this as a difference for delta H, and I can find the potential energy difference based off that new height. So feel free to redefine the H wherever it's convenient for you. You're going to see a better example of that in this next example. Let's imagine we have a very uneven staircase here. So I have a 5 meter high step, a 2 meter high step, and then just 0. Okay, so this height here currently is 5 meters from the bottom step. This one here, not to scale, 2 meters, and this one's bottom step. Naturally, you would go, okay, because this is the very lowest step, let's call this H equals 0. Let's set the ground level this time to be here. If the object is currently here, I try to do an MGH. EP is supposed to be MGH. Let's just keep some numbers to this here. Let's say the mass is 1 kilogram, so I multiply 1, no problem. G, I can assume it's 9.8, which is on the Earth's surface here. I'm going to go 1 times 9.8, well, times the height of 0, I'm 0 joules. I have no stored energy. If you run the clock, I'm just going to sit there. Now what I'm going to do is I'm going to imagine lifting this object just like we did. Let's lift this object to the height of being 2 meters off the ground. So now my second time here when I do this EP is still equal to MGH. I'm still the 1 kilogram. I'm still multiplied by 9.8, but this time I'm now 2 meters off the ground. So this time I actually have some stored energy. That energy came from whoever lifted this object upwards. Relative to the ground level, which is 2 meters below, I'm now 19.6. If you run the clock and drop it, this one here is going to end up falling. It's going to exert a force over distance. It's going to actually apply some work. So that makes sense because it's relative to the ground level. What if I took that same height though, and what if I put that object on the second step though? Suddenly, the object is now being balanced by the normal force. Suddenly, the object can't fall anymore. Suddenly now my EP is now going to be 0 again. I thought we said it was 19.6. How come it's 0? Well, again, it depends on what relative height you're measuring from. Relative to the ground, yes, I do have 2 meters to fall. I would have 19.6. If the ground has come up to match me, if my new ground level is H equals 0 is up here, I can call myself relatively 0 again. So you're going to see that this number here, it's always relative to whatever I call ground level. So depending on what I set to be my H equals 0, this number here might change. Fortunately, though, it's just a relative comparison. We can do the one last calculation. Let's say it's up to the height of being 5 meters tall. Kept the numbers fairly simple. EP is still a mass of 1 kilogram times 9.8, but this time I'm 5 meters tall. That should give you 49. If I have the whole distance of 5 meters to fall, I have 49 joules of energy that's being stored. Again, if I put this one here on a step that's 5 meters tall, suddenly my EP drops to be 0. That's sort of like resetting my H equals 0 to be here. So I'm not comparing it to the ground level anymore. The new ground is actually right up with me. But I can also compare it. What if it's the distance that's just 3 meters off the ground here? I can go the EP in this sort of middle section here. The EP is still, the formula is easy. It's just MGH, 1 times 9.8. The height difference I'm looking at is the 3 meters times 3. This one gives me here 9.8 times 3, 29.4. So just with that example, I just wanted to introduce to you, first thing, the importance, you can reset the 0 no matter where it's convenient for me. And by resetting that 0, you might find that the numbers will actually change. When I was at this height, I'm either 19.6 or I'm either 0. It depends on which H equals 0 I'm talking about. Fortunately, though, the difference is going to be the same. So for example here, we had 29.4 that was stored because I was 3 meters higher. This difference here, if I took 49 minus 19.6, 49 minus 19.6 likewise gives me 29.4. Relative to whatever your new ground level is, the difference is always going to be the same, right? So hopefully that just sort of validates for you here. You can put H equals 0 wherever you want. Right? Let's just flesh this out a little bit more with the 2 other questions here. First question, so we'll do that lifting the object again here. First situation, a crane lifts an object at constant velocity. Constant velocity is the easiest setting right now because there's no acceleration, there's no net force or anything. Crane lifts an object at constant velocity, a distance or a height 490 meters high. If the mass is 500 kilograms, just making up some numbers here. If the mass is 500 kilograms, and it takes 10 seconds, okay, I want you to calculate, similar to yesterday, calculate the work done by the applied force, calculate the work done by gravity, and calculate whether there was any overall or net work that was done. Right? So as always, I like starting off with a picture if we can here. We're going to start off with our object. We're told that it's 500 kilograms. If I wasn't given that mass, I'd just call it an M. Hopefully the M would cancel out somewhere along the way. The 500 kilogram here, it's going to be pulled upwards. We're going to assume just as perfectly upwards. So it's going to go upwards at a constant velocity. Remember, constant velocity means no acceleration, no net force. So if I look at my free body diagram here, just like we just did here, force of gravity is m times g. So this one here is going to be 500 times 9.8. 500 times 9.8 gives me 4,900. For me to exactly pull constant velocity, I can't have too much of a wind. I need to pull slightly harder than the 4,900, but just numerically here, I just say 4,900. I want to make sure that there's no net force to make sure that the thing goes up at constant velocity. This object here, I'm told the distance that it goes is 490 meters high. So it's going to end up somewhere up here. We can do this in terms of the force times distance because I have a bunch of force ones and distance. That's what we're going to do first. And then I'm going to show you how you can also do this with potential energy. So first formula here is simply work is equal to force times distance. If you want the work done by the applied force, take the applied force times the distance. In this case here, the applied force, I was actually doing 4,900. The distance I lifted up is 490. 4,900 times 490 gives me 2401000. Okay. So 000. 2401000 joules. Okay. So energy is a scalar, so it's going to be a positive number. That's the work done by my applied force. What about the work done by gravity? This has to be the gravitational force times the distance here. Gravity is actually pulling downwards. On the free body diagram, the arrow is supposed to be down. When I punch it back to my formulas, I'm actually going to type in negative 4,900 times it by the same 490. As this object here is lifting upwards, gravity is constantly, let's say it's midway up here, gravity is pulling down. Gravity is pulling down. Gravity is pulling down through this whole 490 motion as well. Shouldn't surprise you here. This is negative 2401000 joules. And then surprisingly here, what's the net work that was done? Right? The crane has done something, but if you do the net work, you can either do net force times the distance, or you can just go, well, because my crane did this and gravity did this, I'll subtract these two here. In both cases, my net work is actually 0. It's like I've done nothing. But then you'll say, well, I have done something, right? I've lifted the object upwards, I've stored some energy. If you actually counteract for gravity, because we did this so slowly and it was at constant velocity, it's as if I got no net win, right? I put in this much energy and all of it was supposedly stored, but all of it was taken away based on gravity as well. So if it's constant velocity, I would expect no net force, so no overall work that's done. Even though my crane literally had to do something, my crane actually needed to lift it up by this number here. I can do this with potential energy as well. So work is supposed to be a change in energy. So in this case, here's gravitational energy. I can do a mgh final minus mgh initial. Usually in these problems, the m and the g are going to be constant. So I'm just going to pull those out in front here. mg, I'm just looking at that comparison between how different are hf and hi. My mass is 500. My gravity force is 9.8. I multiply it by my hf. I'm going to be 490 up from my ground level, which is 0. And this one here actually ends up giving you 9.8 times 490 times 500 gives you here that same number, no surprise, 2401000 joules. And if you match this up here, essentially what I'm saying is if I am this far off the ground, this is the amount of stored energy inside. Because this amount of stored energy was delivered by my crane, it gives me this number. But you notice it doesn't quite capture everything. It doesn't capture the fact that because we are actually constant velocity, it doesn't remember that gravity actually went against you. Gravity actually removed a lot of that energy as well. And so the net force is actually 0. Net work is actually 0 as well. So just be careful as you use these formulas. Definitely we do have amount of stored energy because I am lifted yay far off the ground. In this case here, because we are constant velocity, I can just use a d is vt kind of formula. If the distance I traveled was 490, I was at some constant velocity, I was given 10 seconds, I can actually calculate the velocity as 49 meter per second. So for me to get that high in 10 seconds of time, I know it was constant. I know I'm not applying any overall acceleration to it, but I needed to pull it up at a velocity of 49. Let's change the question a little bit here in part B. So let's do the same crane. It's lifting the same 500 kilogram load, but this time what we're going to do, a crane lifts the 500 kilogram load. Load is just another fancy word for object. Okay. But this time what I'm going to do is I'm going to actually pull it harder than gravity with an acceleration. It's actually going to speed up an acceleration of 5 meter per second vertically. I'm just going to remind you that this is just straight up and down. Same question here. I want you to calculate the work done. Calculate the work done in 10 seconds. And of course, we can, again, separate the applied work, the gravitational work, and then the net work. We'll see what we get in this question. So again, similar problem. We have our 500 kilogram load. This time what we're told is we actually have an acceleration. We actually do have a net force, 5.0 meter per second squared. This object eventually, after 10 seconds, is going to be somewhere up here. It's going to have traveled some distance, although they're not telling me what the distance is this time. We can try doing it as a sort of a forces sort of problem. We can still do force of gravity, no problem. Force of gravity is going to be 500 times 9.8. This part here doesn't change. The Earth still pulls that 4,900 on it. But this time, I don't actually know that the applied force is going to be 4,900. In fact, what actually has to happen is my applied force actually has to win against gravity so that I can have a net force upwards. That gives me this acceleration here, so net force. So let's see what we get here. We have the F net. This is just trying to do it with sort of chapter 2 stuff. We'll see how far we get. So bigger number minus smaller number, FA minus FG. The F net is supposed to be given by Newton's second law, which is m times a. FA, I don't have a formula for it, but I do know the FG I calculated to be 4,900. Let's punch through the numbers here. 500. I have a win of 5 meter per second upwards. FA minus 4,900. Just crunch through the math there. The FA, I know it's going to have to be bigger than gravity. It actually has to be bigger by, was that 2,500? So that gave me 2,500. So 2,500 plus 4,900. The FA actually has to be 7,400. Right. So this is sort of the forces way of doing the question here. Great, we now know all the forces. I know the FA, I know the FG. I even know the net force actually has to be 2,500. But what we then need here is actually the distance. So still a little bit of kinematics for you here to figure out how high does it get upon accelerating for 10 seconds. So you can use our kinematic formulas, use an equation that actually has acceleration inside, because this is not a basic motion question. You can assume the object was just minding its own business. It was at rest, so this term here dropped away. The distance that I travel is going to be 1/2. The acceleration, normally I would have said 9.8, but remember what we're tracking here is upon accelerating, after compensating for gravity, I still have a win of 5. I'm going to do 5 for 10 seconds to figure out what this is. So 5 times 10 squared divided by 2 gives you 250 meters. Let me double check that. 0.5 times 5 times 10 squared. So 250 meters. Given 10 seconds of this acceleration, having started from 0, I go to 250. I can then do my work calculations again. I can say, well, work done by my applied force is my applied over this distance. My applied was 7,400. I know some of it was lost due to gravity. Times it by 250. 7,400 times 250 gives me here 1,850,000. The work done by gravity, right? That's just gravity trying to fight against you. Gravity pulls downwards as this object is lifting up. Gravity only pulls 4,900. I'm going to put the negative there because this is going to remove energy from my system. 4,900 times 250 gives you 122,500. And then I can do the net work here. Net, again, you can either take this number minus this number here, or you can figure out, well, what was the net force? The net force would have been FA minus FG anyways, times it by distance. My net force was 2,500, so I have a net win of 2,500. This is another example of these things here adding linearly. So there's no fancy squares involved or anything like that, just like we saw for momentum. And we get an overall work that's done 625,000 joules. Right? So you see, again, we can solve it with kinematics, not a problem. Let's try to compare it with energy as well. So energy was another way of formulating it. I got the work through the force times distance. Let's try it using work equals change in energy. In this case here, change in energy in general, so let's just say or. In general, it should be E final minus E initial. This is going to get us into some of the new stuff we do in the next question here. We need to figure out what are all the types of energy at the end and what are all the types of energy at the beginning. So far, I've only given you two types of energy. One is moving energy and one is potential energy. What I want to do is I want to go, do I have moving energy at the end? Do I have stored energy at the end? Minus, do I have kinetic energy initial plus potential energy initial? Where that formula came from is basically these are the two types of energies that we have, and I'm still comparing the final minus the initial. So at the end, I definitely know this one here has been accelerating. This one here definitely has some velocity. So up here, I would definitely have some KE final. I'll also have some PE final because I'm off the ground. On the ground though, I was at rest, so my KE initial is actually going to be 0 joules. I actually have no motion to begin with, and I also have PE initial in this question of 0 joules. If I set my ground level to be the true ground, I'm just on the ground. I'm not going to actually do anything. So in this case here, essentially what I want to do is I want to go, it's going to be 1/2 m, what's your final speed squared? We still need to calculate that, plus mgh when I'm that distance off the ground. In this case here, we were at rest, so I have no moving energy at the beginning, and I was actually on the ground. This is not true for other questions, so just 0 and 0. Once I find this velocity here, that should be all the numbers that I need. I already have the distance, so I can use that and I can match it up to what it actually calculates for me. So again, a little bit of kinematics. We have the acceleration, we have the distance, so let's do v squared equals v naught. I can even go v equals v naught plus at. You could do v squared equals v naught squared plus 2ad just to verify. So in this case here, I'm looking for, I know I've been constantly changing speed, but what I'm looking for is I'm looking for this speed you are exactly 10 seconds later. So if I were starting out at 0, my acceleration rate was 5.0, I'm 10 seconds later, this gives me 50 meter per second. I know it was constantly changing to 50, it was like 10 meter per second, 20, 30, but by the top it was 50. You can verify that here, make sure this gives you the same thing, plus twice times the acceleration. The distance that we got earlier was a distance of 250. Right. So hopefully that gives me 50 again, 2 times 5 times 250. Oh, let's see. Oh, that's 2500. That's v squared, so then v is the root of that. So 50, perfect. So at least the kinematic equations are consistent. And now we're ready to punch it back into our change in energy formula. If I did 1/2, the mass was 500. Double check that. Times it by your velocity. By the time I'm 10 seconds later, I'm actually traveling 50. Plus it by an mgh, 500 times 9.8 times the height. I'm now 250 meters off the ground. I'm going to figure out these separately here for you. So 0.5 times 500 times 50 squared. This part here is 625,000. 500 times 9.8 times 250. This part here is 1225000. As you're matching up some of the numbers, you actually start seeing some numbers match up here. You'll notice the kinetic energy part coincidentally, it was similar to the network. This part here is coincidentally similar to the amount of gravitational. This is just for comparison's sake. You normally wouldn't have to do this. So you add 625,000, and similarly, just like in the earlier question, we end up with 185,000, and this is probably the one that you do need to know. In this case here, by doing work as a change in energy, again, we have been able to find the work that's done by the crane, totally forgetting about the gravitational part of it. So hopefully that helps you introduce to you potential energy. We start formulating in the two different ways, either more simply work as force times distance when we're given all these arrows and distances here, or we're going to see sometimes questions will only give you energies, so you have to do it with energy in this case. Just to introduce two last concepts here based on this problem. I know that my crane supplied this amount here. I can actually define two things for you. One is I can define another concept called power. Power, by definition, Power is actually the rate at which work is done. So it's how quickly you can actually deliver this work. The job took 185,000 joules, okay? But if I took 10 seconds to do it, you actually have this formula on your formula sheet as well. If you know the job took this 1850, remember that part there ignores what gravity does. Gravity's just going to go against you anyways. This right here divided by the 10 seconds that you pulled it at, this gives you another number, 185000. This unit would have been joule per second. That means for every second that the crane is actually pulling this upwards, let me actually write this in words here. The crane supplies 185000 joules every second. It does that for 10 seconds of time, which gives you the overall job, which took this much. The crane overall did 185000. That has now a power rating of 185000 joule per second. The advantage of doing this power here is as it's intensive. So if I ran the crane for 20 seconds or 30 seconds, I can figure out what sort of job I can do with that added amount of time. This unit here, joule per second, is a little bit cumbersome to write. So I'm going to define this one here as the watt. Watt is going to be capital W. So this one would have been worded 185000W, and that's how much energy was delivered. So power is a little bit of a spin-off. The other spin-off of it is something called efficiency. We're going to deal with this a little bit more if we look at simple machines later on. Efficiency is basically, I know what the task took, but usually because of some losses to the environment, my efficiency may not necessarily be 100%. So this one here is a comparison. Compare the actual energy input. So I write it in words here. Compare the actual energy input with the energy output. So maybe the crane was supplied by electricity, by burning the fuel and whatnot. I know the job in this situation took 185000 joules. That's the task for lifting this object upwards. But maybe if I just track my electricity bill, maybe my electricity bill, this number would have had to be given to you here. Let's say the electricity I used for this same task was actually 200,000. Okay. Not surprisingly, I didn't get all the energy delivered for the motion that I wanted, but I can actually calculate this efficiency. It essentially is a ratio. It is given a very funny symbol. It's the symbol eta. It's like a squiggly n. And basically, we're just comparing here energy of the task divided by how much energy input there is. This is just a ratio, so later on I can go work out divided by work in, or power out equals power in. In this case here, because I have it quoted as energy, I would just simply go, well, I got a task of 185000 joules. I had to supply 200,000 joules though. This would give me a fraction, so I'm going to multiply by 100, so I get 100, get it as a percentage. 185 divided by 200 essentially gives me an efficiency of 92.5%. Of the energy I put in, this 2 million joules of energy, only 92.5% was actually used to actually lift the object upwards for what I wanted. Obviously, you want to tweak some conditions to try to maximize efficiency if you can, but that's what that problem shows you here. So overall, we've introduced potential energy. We talked about how you can reset h equals 0 to something convenient. We did a few problems where we could still do work as force times distance or work as a change in energy. And there are these two last little spin-offs here. You can actually calculate the power, how much work is delivered in a given amount of time. Obviously, something that's more powerful will deliver more energy within every second. And efficiency is I'm always going to be expecting some energy losses, but because the energy ends up getting lost, we end up not getting 100% of what we put in. Let me leave you with this last question just for you to practice here. Okay. So this question here, you can think about whether the work times work equals force times distance formula works better or change in energy works better. So this time I'm going to give you, there's a plane. The first plane is 20 meters off the ground. The plane itself, let's just make it a very light plane. So 100 kilograms, it's a toy plane. It's traveling at 50 meters per second. That's the initial. And what it does is by firing its engines and whatnot, it ends up climbing to a distance total of 70 meters. And it ends up, it's still the 100 kilogram plane, the plane is still intact, and now it's actually traveling faster. Let's make it go at 65 meters per second. I want to know how much work was done. So this is initial, and this is final. I want to know how much work was done was taking the plane from this initial state to this final state. How I might do it here is just giving a few hints here. So find the work done to go higher and faster. Hopefully you understand that based on the picture there. If you set h equals 0 to the bottom here, you can have, well, this is moving energy. So this is kinetic energy initial and potential energy initial. This one here has kinetic energy final. It's still moving. Potential energy final, because it's still 70 meters off the ground. You can do that change in energy sort of formulation. Or if you can just compare for yourself, you can reset the h equals 0 to be here. If I reset h equals 0, this is now my new height, then I can drop this term from the first part, but this potential energy diagram would just be the difference in height, so this would just be the 50 meters. Try it both ways and see if you get the same answer. You should be able to find the work taking from initial to final. If you have any questions, just let me know. Thanks, guys.